Welcome back to Domain 3 of the Security Plus Exam Cram Series 2024 edition. And here in the fourth and final installment of Domain 3, we'll focus on high availability concepts. We'll talk through the different types of disaster recovery sites. We'll discuss the nuts and bolts of business continuity planning before covering an array of backup types to protect our data and our services. And we'll wrap with a discussion of capacity planning and testing of our resilience and recovery mechanisms. Resilience and recovery are key elements in supporting availability, and when it comes to the CIA triad, confidentiality and integrity are nothing without availability. It's the third leg of the tripod that keeps it upright. Let's dig in. Welcome back to the Security Plus Exam Cram Series 2024 edition. And in our continuing coverage of Domain 3, we'll wrap this domain with Section 3.4, focused on resilience and recovery. More specifically, we're expected to explain the importance of resilience and recovery in security architecture for the exam. So in this section, we'll explore high availability concepts, site considerations, including the types of disaster recovery sites we might choose from, the importance of platform diversity, multi-cloud systems, and continuity of operations. We'll take a look at capacity planning concerns, the different disaster recovery testing types, an array of backup strategies, and finally a look at power. Before we do, though, I want to unpack those two terms we see in the title of this section, resilience and recovery. I don't want to take for granted that we know the details of these two and the difference between them. Resilience speaks to the ability of a system to remain functional even when faced with unexpected events like natural disasters or cyber attacks that lead to disruptions and failures. Resilience is delivered through redundancy in systems and failover mechanisms in the event of system failure. But this is a security exam, so let's get a bit more specific. Cyber resilience refers to an organization's overall ability to prevent and withstand cyber threats and incidents. It's about ensuring continuity of operations even during attacks, disruptions, or outages. And then we have recovery, which focuses specifically on the restoration of data and systems after a cyber attack or incident. Stated a bit more simply, it's the process of getting things back to normal after a disruption. So some of the key elements of recovery include backup, disaster recovery, business continuity planning, testing, and validation. We will certainly touch on backup and testing in this section, and we'll dig into disaster recovery and business continuity planning at greater depth later in the series. But since resilience and recovery are the two elements we're evaluating throughout this section, I want to just paint a picture for you here. So think of resilience and recovery as two sides of the same coin. Cyber resilience is the shield. It protects your organization from attacks and minimizes the likelihood of successful breaches. Cyber recovery is the repair kit. It allows you to fix the damage and get back on track after an incident. The goals here are to improve the organization's overall cybersecurity posture and to ensure business continuity even in the face of cyber threats. So you might think of resilience as being a proactive measure and recovery being a reactive measure, though we're going to take some proactive steps to prepare for recovery to make sure we can recover when we need to. The situation call for it. So let's get into high availability, and we'll start with load balancing, which distributes network traffic across multiple servers, ensuring optimal performance and high availability. So from a resilience perspective, it distributes the workload by spreading traffic across multiple servers. Load balancing prevents overloading any single server, ensuring continuous operation even if one server fails. Load balancing also simplifies scalability. It allows easy addition of new servers to handle increased traffic, enhancing responsiveness and preventing bottlenecks. Generally speaking, when I want to add a new server to a load balance web farm, it's a pretty easy operation. I plug the server in, I add an entry to my load balancer table, and I'm all set. And it allows us to scale out, adding additional servers, which is a less expensive strategy when we're using that in the cloud. So we can add additional servers when we need the additional capacity, or at least shut them down and start them up, rather than simply oversizing a smaller number of servers with excess compute, which in the cloud we'd have to pay for. So let's look at load balancing from a recovery perspective. So we get faster failover. When a server fails, the load balancer automatically directs traffic to remaining healthy servers, facilitating quicker recovery and minimizing service impact. And it simplifies recovery. By isolating individual failed servers, load balancing simplifies the process of identifying and addressing the issue on the failed server without affecting the entire system, because the load balancer removes failed servers from the list of available servers in the farm that are receiving requests because they fail the health check. And load balancers are commonly used with front-end web and application servers. So hopefully the type of health check is one that makes a call to the application to make sure that it's serving up content and it's not just a simple ping check. So let's move on and talk about high availability in the context of clustering now. So clustering combines multiple servers into a single, highly available entity, ensuring continuous service even when individual servers fail. So from a resilience perspective, we have hardware redundancy. So it creates a single logical entity from multiple servers with shared resources and data. Traditionally, we'd configure server clusters with shared data behind them. Increasingly, that's not always necessary nowadays, but oftentimes there are shared resources and data on the back end, and if one server fails, the others can take over the workload, take control of the storage, continue to serve up data and resources. So we're also getting high availability here. It provides continuous uptime even during individual server failures, preventing any disruption to service. And from a recovery perspective, we get automatic failover. Basically, when a server fails, the remaining servers automatically take over its tasks, ensuring seamless service continuation and minimal user disruption. You typically put an odd number of nodes in a server cluster and they establish a quorum, and when a majority can't contact a specific server, they take it out of the cluster and continue service without it. And oftentimes, we'll see data replication come into the picture. So it's often implemented with clustering to ensure that data is stored on multiple servers, allowing for quick restoration in case of data loss on a single server. But we'll also often see data replication to a cluster at a recovery site, which potentially gives us a way back if there's something very unexpected that happens with that cluster on the whole. For example, if that cluster uses shared storage and we have a major storage problem that causes all the servers to go offline. But you'll see clustering typically used with back-end database servers. So if you have a web application with back-end databases, you're typically using load balancing of a web farm or an application server farm up front, and you're using clustering for your databases in the back. So using physical or virtual servers in both front and back end, but how you establish that high availability is different based on their role. Okay, next on the syllabus is multi-cloud systems. So from a resilience perspective, what we're talking about here is distributing data and applications across multiple public cloud providers to create redundancy and fault tolerance. So if one cloud provider experiences an outage or an attack, the others can maintain service for us. It allows us to keep the trains running, servicing customers, while we recover whatever has failed in that affected provider. And from a cyber attack perspective, it indirectly works as a method of segmentation, because when AWS is affected, Azure and Google Cloud Platform would likely remain unaffected. But from a recovery perspective, this buys us a great deal because it enables rapid failover to unaffected cloud platforms, minimizing downtime and facilitating faster recovery from security incidents. This might mean simple DNS failover, or we can actually deal with failover automatically in some cases with global load balancing strategies. We could even implement a global server load balancing strategy with a third party like Cloudflare, so we can route across all of our public cloud providers, basically sending traffic to healthy server pools no matter which cloud they're located in. From a cyber risk perspective, what multi-cloud does is mitigate the risk of vendor lock-in and provider-specific security vulnerabilities. In this same vein, let's talk about platform diversity. So platform diversity very much mimics what we talked about with multi-cloud, but it focuses on utilizing a mix of different platforms. We're talking about operating systems, software vendors, cloud providers, so it's a broader strategy, right, that reduces reliance on any single point of failure, any single vendor. If one platform or provider experiences an outage or a security breach, the others continue functioning, minimizing disruption. And same sort of strategy. It allows us to recover more quickly by allowing operations to shift to unaffected platforms while the compromised one is addressed. And it mitigates platform-specific vulnerabilities or attacks. So whether it's a SaaS provider or a public cloud platform or a sudden zero-day threat on a Windows or Linux operating system, we're mitigating the risk. Next, we have continuity of operations. So from a resilience perspective, what this means is planning, outlining procedures and resources to maintain critical business functions even during disruptions. This would include backup and disaster recovery strategies, alternative communication channels, and other disaster recovery protocols. So this is all proactive work to ensure that when recovery happens, we have a swift and efficient recovery process, minimizing downtime and financial losses after security incidents. Basically, ensuring that operations response is successful, reducing the potential for loss of any kind, whether data, financial, or something else. Okay, now we're going to move on to site considerations. Recovery sites are secondary locations where critical IT infrastructure can be restored, ensuring business continuity after a major disruption at the site level. So in terms of resilience, recovery sites give us a contingency plan. It provides a backup option in case of catastrophic events like natural disasters or cyber attacks that affect an entire site. Simply put, it minimizes downtime due to site failure, and it enhances our preparedness for these types of events. It improves the organization's ability to maintain business continuity through unforeseen circumstances. And from a recovery perspective, it gives us faster restoration. It allows for quicker resumption of critical operations compared to rebuilding everything from scratch at the primary site. And it also gives us reduced downtime. So it minimizes the impact of disruptions on business activities and revenue generation. Now, to be clear, budget and availability needs will dictate the type of recovery site we implement, or recovery sites. So from that perspective, we see 3 types of sites called out in the syllabus, and those are hot, warm, and cold sites. And there's room for a lot of nuance in creating hot, warm, and cold sites. They're not all the same, but I'm going to give you the high-level definitions that will allow you to focus in on the core intent for the exam. So let's start with the cold site. So this is a recovery site that is essentially just data center space, power and network connectivity ready and waiting when you might need it. So to recover, if disaster strikes, your teams can basically move your hardware into the data center and get you back up and running. So from a cost perspective, it's low. From an effort perspective, it's high because we just have the space. Moving on to the warm site. So a warm site is more preventative in nature. It allows us to pre-install hardware and pre-configure our bandwidth. So to recover, all we have to do is load our software and data to restore our business systems. So the cost is going to be a bit more, and the effort is going to be a bit less versus the cold site. So I'd say cost and effort are both in the medium category. And finally, we have the hot site. A proactive hot site allows you to keep servers and a live backup site up and running in the event of a disaster. You replicate your production environment in that data center. And to recover, we have a near immediate cutover option when we have an affected site. So in the case our primary goes down, cutover should be momentary. So for mission critical sites and mission critical customer facing services, a hot site is considered a must for organizations that can afford it. This is going to be the highest cost, but the lowest effort in recovery when it's time to execute. The last item on the discussion list for site considerations are geographic considerations for our recovery sites. We need to think about our data, systems, services, as well as the personnel who will execute the recovery operation. So distance is certainly a concern. And while the fastest site to restore services is a hot site, a site hundreds of miles away is sometimes impractical or inconvenient in some respects. But location is important. The location of the hot site is critical to the speed of data, system, and service recovery. Now, the considerations for personnel may vary because we can often work remotely. And that location should be far enough away to ensure recoverability in the event of a natural disaster like a hurricane or a tornado. And your public cloud providers are a great example to follow. Your CSPs definitely ensure they're far enough away for recoverability when they pick their own primary-secondary pairs. In fact, they typically maintain 300 plus miles between sites. So it's pretty common that for a cloud service provider in the public space like AWS or Azure, they'll have a primary site, say, on the East Coast, and the secondary failover site will be on the West Coast. And especially if you're in a hybrid or private cloud situation, you have to think about off-site backups. We have to have backups off-site, meaning physical backup media should be stored in a fireproof safe somewhere or safely in the cloud if it's still digital. And I would say today that is the most common approach. It's pretty rare that we see folks using tape all that much anymore. And similarly, disk-based backup should be stored off-site in a cloud or other secure remote repository, but cloud services are a very common solution today. Next up is capacity planning, and the capacity planning topic has 3 subcategories listed on the syllabus: people, technology, and infrastructure. So let's start with the definition. What is capacity planning exactly? Well, it is the process of proactively assessing and ensuring an organization has sufficient resources, like people, technology, and infrastructure, to meet current and future demands, preventing performance bottlenecks and service disruptions. Preventing is a key word there. So let's start with people. We need to ensure that the workforce possesses the necessary skills and knowledge to maintain secure systems and to respond to security incidents. And we also need to make sure that the workload is manageable. We need to manage staffing levels, turnover, and sharing that workload across the team to optimize results. At the end of the day, the goal is a skilled workforce who can identify and mitigate security threats. And next we have technology. So we need to ensure that the software and tools with appropriate features like automation to enable analysts to manage incidents at scale are in place. Implementing and maintaining appropriate security software and tools like firewalls, intrusion detection and prevention, anti-malware, vulnerability scanners. At the end of the day, these security tools enable the security teams to respond appropriately at scale. And the right tooling with the right capabilities and enough licensing to run those legally is very important. And then we have infrastructure, so ensuring adequate system level resources, storage, networking, processing to handle peak loads. So ensuring elasticity to respond to sudden spikes, like in the midst of a disruptive attack of scale, like distributed denial of service. This enables faster response and reduces the potential for loss of any kind, data, financial, or otherwise. The next category on the syllabus is testing, but it's clear that we're talking about types of incident response exercises here, and there are 4 that you should know for the exam as called out by the syllabus. There's the tabletop exercise, sometimes called a structured walkthrough, where you distribute copies of the incident response plans to the members of the incident response team for review. The team members provide feedback about any updates needed to keep the plan current. It's something that usually happens in a conference room together. It's paper-based, it's hypothetical, it's talking only. Usually only the person leading the tabletop exercise knows what they're going to be talking about before the meeting. And that person will put some sort of scenario out there and the team will talk through the response plan. Then we have the failover plan. This is where tests actually shut down the primary site and test whether the recovery site properly handles the load. So, of course, this should be carefully planned and scheduled as they can impact production operations. And then we have the simulation, which are functional exercises that allow personnel to test the plans in a simulated operational environment. These functional exercises range from simple simulations to full-blown tests without affecting production systems. The tests will cover specific pieces of failover in a simulated environment is the key here. Meaning doesn't touch production. And then we have parallel processing, which ensures the disaster recovery site is actually working by activating it during the test. So during the test, the recovery site starts operations and runs alongside the main site in parallel, which enables testing the plan in something that feels like a full test, but with less risk than a simple full failover. Now we're going to move into the backups category, and you need to know what each of these backup types do, but also why they are important to security. So I'll fill in the gaps on all counts here. So backups can be on-site or off-site. So your on-site backups are stored on the same physical location as the original data, like an external hard drive. Off-site backups are stored in a separate location, cloud storage, remote data center, secure off-site storage purpose-built for storing media of that type. And then there's the backup frequency, which refers to how often backups are performed. It might be daily, hourly, continuously. The frequency really depends on the importance of the data, the amount of the data changing, acceptable levels of data loss, and for critical data that allows us to keep the business running, the backup schedule is going to be more aggressive. And we'll talk about recovery time objective and recovery point objective, RTO and RPO, later in the series in some depth. But your backup strategy is going to be influenced by the amount of data you're backing up, the amount of data churn there, and how much time and data we can lose in case of a disaster and still resume business in a new location or on a new system. Next we have encryption. So this is the process of scrambling data into an unreadable format requiring a decryption key for access. Sensitive backups should not be left in a plain text format. They should not be plain text human readable. Next we have the snapshot. These are point-in-time copies of data at a specific moment, allowing recovery to a specific state. Snapshots are very common with VMs and with high-end storage area networks. So we need to think about recovery, the process of restoring data from backup to its original location or a new location. And this really refers just to understanding the process of restoring data from the backup. There needs to be some advanced planning, some of that recovery planning to make sure that we understand what the potential needs are in different scenarios. Are we always going to be recovering to the original location? Do we need a strategy to recover to the new location in a specific amount of time? We have replication, creating identical copies of data in multiple locations for redundancy, and journaling, transaction logging, recording all changes made to data in a sequential log file. And this log can be used to recover data to a consistent state by replaying the log transactions, enabling point-in-time recovery or roll-forward recovery. But that replaying of log transactions is actually pretty common with some relational database recovery strategies. So point-in-time recovery would recover the database to a specific point in time, and roll-forward recovery would bring it up to typically like right before the moment of the critical failure. So we've talked about the what when it comes to backups. Now let's talk about the why. So why are backups important to security? Well, naturally, backups are crucial because they provide a way to recover data lost due to various security threats. So it may be accidental deletion, hardware failures, or very intentional, like ransomware attacks or other incidents. Backups give us a means to restore data and minimize the impact. And some cyber attacks, like malware and ransomware attacks, ransomware in particular, often encrypt or corrupt data, making it inaccessible. Backups stored securely off-site can provide clean copies for recovery. Stored in the cloud may allow us to recover cleanly more quickly. Compliance requirements can also mandate data backup and retention for specific periods. So backup ensure compliance with these regulations. And if you're asked on the exam, a full backup provides the fastest recovery time. The real answer is going to depend on the nuance of the situation, but on the exam, if you get a generic question about fastest recovery time, it's almost certainly going to be full backup they're looking for. I think we've covered the spirit of these all already, but I'm just going to roll back some scenarios here so you've got them written down in one place as you prep for the exam. So ransomware attacks. After a ransomware attack, backups allow for data restoration without paying the ransom. Super important. Very likely real-world scenario. Disaster recovery, so in case of natural disasters or infrastructure failures, offsite backups ensure data availability. Accidental data deletion. Data corruption, so we can use backups to restore data corrupted by malware or even hardware malfunction. And I mentioned compliance. We could also use backups for compliance audits to demonstrate adherence to data retention policies and regulations. What you'd see in an audit scenario is a request from the auditor to restore a specific piece of data from a specific point in time. So we'll wrap up 3.4 with a look at power. So we're going to talk about the need for clean power. So power supplied by the electric companies is not always consistent and clean. Most electronic equipment we're working with in a data center requires clean power in order to function properly and avoid damage. So a UPS is a type of self-charging battery that can be used to supply clean, consistent power to sensitive equipment and supply that power for minutes or hours depending on its size in the event of power failure. But it's important we understand the difference when it comes to power redundancy between the purpose of a UPS, the uninterruptible power supply, and a generator. So a UPS is essentially a battery that is a standby device so that when primary power fails, it provides power. It's really designed to keep the systems running for a limited period of time, though, basically to enable graceful system shutdown. It's also used to clean up the power coming from the grid, eliminating spikes, surges, and voltage fluctuations. It protects systems and data from damage. We then have the generator, which is a standby power source that is powered by diesel, gasoline, propane, or natural gas. And when power from the grid fails, it can be started to provide electricity for an extended period of time. Generators are used by hospitals, data centers, and other facilities hosting critical services. But a generator provides sustained alternate power to support continued operation, not just graceful shutdown. So the UPS, while it's cleaning up power, preventing surges and voltage fluctuations, in the event of a failure, it's short term. It's minutes or maybe hours. The generator is going to be longer term, hours or even days. But in either case, it allows us to respond more effectively and gracefully to an unexpected loss of power, regardless of the reason, resulting in a reduced risk of data loss and a reduction in the time of our service outages, or potentially avoiding that outage altogether. My friends, that brings us to the end of section 3.4 and indeed the end of domain 3. I hope you're getting value from the series. As always, if you have a question, leave me a comment in the space provided below the video. Reach out directly on LinkedIn. I'll look forward to seeing you back here for the kickoff of domain 4 in the next couple of days. And until next time, take care and stay safe.